Hello and welcome to the second part in this series. In the first part, we saw model preparation and setup features on the front wing assembly for external flow simulation in the 3D Experience platform. In this part, we'll explore some additional model preparation features, this time on the full vehicle model. This part will also be a good segue into part 3, which will be focused on post processing results from our setup in this part. So let's get started. I'm in my web browser and logged into my tenant. Using the compass, search for and launch the Model Assembly Design application. In the native application, make sure to set the desired collaborative space as leader. Click on the plus icon to import the 3D XML file that is provided to you. This file is titled FSAE Full Car. Make sure to import the file using 3D XML with authoring format. You can choose to add a duplication string for easy identification as well. Another method you can directly import the 3D XML file is by simply dragging and dropping the file from Windows File Explorer into the native application. In the Product Finder application, expand the physical product. Right mouse click SV underscore model and open it in new application. The model will open in the Model Assembly Design application in a new tab. SV underscore model has a 3D shape with an ordered geometrical set called design features, which contains several imported bodies. While this is not an ideal scenario, we will make the most of what we have and create a finite element model required for flow simulation. Double click on SV 3D shape to switch to the simulation model preparation application. Now click on the 3D shape again, and from the toolbar that pops up, select the ordered geometrical set option to create a new one. Right mouse click on this newly created set and using properties, give it a relevant name. Right click on this set and define it as an in-work object. In-work object can be verified by the underline below it. From the check and repair, click on the join command. In the graphics area, click and drag to select the whole assembly for elements to join. This may take a few seconds as this is a fairly large model. Uncheck the check connectivity and check manifold options and click OK to join all the imported bodies. We can ignore the warning about non-manifold edges. Hide the design feature order geometrical set from the feature tree. From the Idealize tab in the action bar, select the Multiple Extract command. Make sure the rectangular trap selection is active for the tools palette. In the Multiple Extract definition, set the propagation type to tangent continuity and select all the faces on the front wing. This way, we'll create a separate feature for the front wing. The multiple extract feature lets you extract sub-elements that are joined into one element. These sub-elements can be curves, points, surfaces, solids, volumes, and so forth. Make sure to select all the faces on the front wing one by one so that there are no free edges remaining. Free edges are highlighted in red color. You can use different standard views to reorient the model to make the selection process easy. I'm speeding up the remaining selection process until a point where we have the faces we need. Once all the necessary faces are selected, click OK in the multiple extract definition window. In the multi-result management window that pops up, check the radio button to keep only one sub-element using an extract. Cancel out of the extraction definition dialog box if it pops up. Right mouse click on the multiple extract feature in the feature tree and rename it using the properties option. If you hide the join operation, you should be able to visualize the front wing extract. Similarly, we'll create another extract, this time of the rear wing surfaces. From the Idealize tab of the action bar, click on the multiple extract command to activate it. Select all the surfaces on the airfoils of the rear wing along with the surfaces on the two end plates. Make sure to have the propagation type set to tangent continuity and click OK in the window to execute the command. Rename the newly created multiple extract feature accordingly. Double-click the physical product in the tree to switch to the model assembly design application and then right mouse click on it to insert a representation. From the window that pops up, click on Finite Element Model under Simulation Model. This creates a new finite element model feature within the product. Select this feature in the tree and using the compass, search for and launch the fluid model creation application. Launch the Contributing Shapes Manager from the action bar and make sure you have checked the right 3D shape to be included in the simulation. Now launch the Contributing FEM Manager to make sure you have the right finite element model included as well. From the action bar, launch the Fluid Domain command. In the window, make sure you set the definition to extract from part boundaries. Click on the plus icon against part to define the boundaries using the specified part. Under support, select the join feature from the feature tree, check the box to allow boundary layers to be added and click OK. Expand exterior boundaries and set the boundary type to bounding box. You can create a bounding box to define the space in which fluid flow around your model. Insert the values for minimum and maximum x, y, and z coordinates as shown. From the View tab, use different view options to visualize the bounding box. Make sure the box is cutting the geometry exactly at the center. As this is a symmetric model, we'll only be using half-car model for simulation to save computational time. In the Fluid Domain window, add a new region. For support, specify a region by selecting the surface that contacts the fluid. A blue cubical glyph indicates which side of the surface you defined as the fluid region. You might have to flip the direction of the glyph to establish which side contacts the fluid. Surface selection helps you form a portion of the boundary faces of the fluid domain. When you include surfaces as part of the definition of your fluid domain, you can also use them as the supports for features you create in the fluid scenario. Create two surface selections, one using multiple extract front wing and the other using multiple extract rear wing. For region, you can point to the blue glyph to specify the fluid region. Now click OK to confirm our fluid domain selection. You can find the fluid domain definition under the abstraction branch within the finite element model in the tree. From the Properties tab, launch the Fluid Selection window. Select the fluid region as support. Search for material, in this case air, and click OK. Please refer to the fluid selection step in part 1 of this series to learn more about how you can import standard materials if you are a first time 3D experience user. From the Mesh tab, select the hex dominant mesh procedure. Specify the minimum and maximum mesh size as shown and check the box to add boundary layers. Click on the local mesh size option for face and edge. Now select the join feature from the tree to define the support. With a mesh size of 5 mm, click OK to go back in the hex dominant mesh window. Now click OK again to confirm our selections. From the action bar, update the model to create a mesh. This command may take a few seconds to execute. From the Display tab, use the Sectioning tool to cut the fluid region. This tool helps you to visualize details that are normally hidden in the interior of a model. Unchecking the exact mesh cut option will highlight the mesh on the cutting plane. This gives you a good idea about the local mesh refinement. You can zoom in on the model on a specific edge, a specific face, or a specific region to visualize the boundary layers. Select the top level physical product and using the compass launch the fluid scenario creation application. In the simulation initialization window, name your simulation and point to the finite element model that we worked on. This physics simulation object contains the physical product with a 3D shape and a finite element model. As you can notice, we haven't defined a procedure yet. Before we define the procedure, make sure you have a green check mark next to the correct finite element model. Launch the physics behavior command from the procedure tab and set the state to fluid if not already, and set the turbulence model to SST K omega. Click OK to confirm your selections and click on the steady state step to launch the definition window. Here set maximum iterations to 400. The step stops if this maximum is exceeded before the solver arrives at the complete solution for the step. Change the momentum, total kinetic energy, and omega error threshold to 0.1 and set sample iteration to 40. This means that the active stopping criteria must meet their threshold over 40 consecutive sample iteration before the app ends the analysis. Click OK. All the features we work on in the fluid scenario creation application show up under the flow analysis case in the scenario section of the feature tree. Let's hide the mesh, and from the boundaries tab, click on the wall command. Select the bottom wall as support and set the wall type to moving wall. Specify a velocity of 60 miles per hour about the negative z direction to simulate relative velocity between the car and the ground. You have the option to enable wall roughness and also specify the roughness height. Click OK to confirm your selections. Similarly, create another wall condition, this time with the top and the side walls with a no slip wall type, which means that the fluid will stick to the wall with no relative velocity between the fluid and the surface. If you want the fluid to not stick to the wall, use the slip wall condition. The slip wall condition is also appropriate for models with symmetry surfaces and zero shear. Use the velocity inlet feature to describe the flow in terms of velocity of a particle flowing through the inlet. Specify the appropriate inlet phase of the bounding box as shown along with the magnitude of velocity. In this case, 60 miles per hour. With the default turbulence intensity and turbulent viscosity ratio, click OK. Notice that the direction of the velocity is not correct. In this case, you can simply double click on inlet velocity symbol and change the direction by removing the minus symbol. Use the pressure outlet option to describe the static pressure at an opening opposite to the velocity inlet where fluid flow out of the region. Select the surface where the fluid leaves the domain as support. Specify the static gauge pressure and click OK. Since the car geometry is symmetric about the YZ plane, we will create a symmetry flow condition as well. Select phase 5 of the bounding box as shown and click OK. The feature manager is a good tool to monitor all step dependent features that are defined. You can also edit the definition using the feature manager. Double click on fluid physics default to change the velocity scale to 60 miles per hour. Click OK to confirm the physics default selection. Let's rename the flow analysis case. Right click on it in the feature tree and launch the properties dialog box. We'll call this flow analysis case 60 miles per hour. Click OK to confirm the selection. Expand output request branch in the tree and double click on the default output, output.1. For frequency of output at every n increment, specify the value of n as 10. Uncheck all the default request variables except the ones under flow and mesh metrics. Click OK to confirm selection for this output request. Now create a couple of history output requests. Use the output option from the simulate tab in the action bar to launch the output window. First, create a request for the total forces on the front wing. From the feature tree, select surface selection front wing to define the support. Switch the output group to history. Expand the flow branch and select fluid force total. Click OK to confirm the selections. Similarly, create another history output, this time to request total forces on the rear wing. Click on Support to activate the selection filter. Then select Surface Selection Rear Wing from the tree. Make sure you have the output group set to History and select Fluid Force Total. Click OK to confirm selection. Right now we have fully defined flow analysis case for 60 miles per hour using a steady state step. But what if you want to study the results at 30 miles per hour as well? In that case, you can simply duplicate the existing flow case and change the velocity to 30 miles per hour. The duplicate analysis case option is located in the Setup tab of the action bar. You can choose a new finite element model for the new case or stick with the one used by the original case. Make sure the new flow analysis case is in works by verifying the underline beneath it. Double-click on Fluid Physics Default in the Initial Conditions branch in the tree and change the velocity scale to 30 miles per hour. Also make sure to change the magnitude of velocity to 30 miles per hour for the moving ground wall and for the velocity inlet. All the definitions of the original flow analysis case are duplicated, including the output requests. Hit Ctrl and S on your keyboard to save the work. This may take a few seconds. Click on Simulate option in the action bar to launch the Simulate window. The simulation can be ran locally or on the cloud. If you have access to the Fluid Dynamics Engineer role, you get access to 16 cores out of the box, both locally and on cloud. You can purchase additional tokens and credits to unlock 244 cores. Click OK to run the simulation. If you choose to run the simulation on cloud, it may take a few seconds to upload the job and acquire resources before the simulation starts running. The simulation status window lets you monitor the progress interactively. The Message tab displays error messages, warning messages, and informational messages, if any. The Licensing Message tab displays information about tokens or credits consumed if the simulation is being ran on the cloud. Click on the Plots tab to display various plots. Switch between plots to monitor the results of different output requested. The Iterations tab displays a table of information about the simulation at each iteration, whereas the Diagnostic Files tab displays the contents of the data file, message file, and status file for the analyses. Once the simulation is successfully complete, check the box to refresh the session and close the simulation status window. In the next part, we'll explore how to post-process results using the Physics Results Explorer application. Thank you for watching and see you in the next one.